office, Vladenia and Cristian Bereanu. And thank you, Oliver, for starting the recording. I was about to warn everyone that the meeting will be recorded, and of course we'll share the recording afterwards. There will be a slot for questions at the end of the presentation, so please write your questions on chat or save them for the last part of the presentation. We have experienced a bit of technical issues with the internet connection in Iași office a bit earlier today. I hope everything will go smoothly. If not, we'll have to adjust along the way. Luckily, Cristian is working from home today, so we have some backup there. That's all from my side. Recording has started, so I'm handing over to Vlad and Cristian.
Okay, hello everyone and welcome. My name is Vlad. I am part of the SAP GDM team. We are specialized in working on e-commerce projects. You might remember me from the last all hands call. If you joined, I did a small presentation also with some with a AI use case for a dashboard or on our e-commerce project. Today, I will present you the very basics of deep learning. So we are going to talk today and Thursday about deep learning in general. And next year in Q1, we will have another series of presentations, maybe 2 or 3, where we will further deep dive into generative AI with LLMs especially. We're going to talk about ChatGPT, Google BERT, and also another model from Google. Yeah, but today and Thursday, I wanted to do an introduction to deep learning, so you can all have a better understanding on how everything started, because all of the models that are popular today, AI models, are based on neural networks. And when we talk about deep learning, we talk about training neural network. So this is what we'll cover today. Today, especially, we'll do the very basics of deep learning. And on Thursday, we'll have a more practical session. We will also look at some Python code, and we will train together some a neural network on the fly. Okay, I will share my screen in a moment with the presentation. Okay, I hope everyone sees my screen and the presentation. Okay, let's do a quick intro on generative AI. I think we can all agree that it has a very big impact on our lives, something comparable to the steam engine, the electricity, or even the internet. But the impact is even more noticeable because we can notice that the evolution is very, very fast. I mean, 1 year ago, today we can have like whole projects analyzed or screen sharing with LLM models from GPT or Google, and they can assist us on the fly. Last year, we could only chat by text. Today, we can also generate images or even videos. In a short while, we can also generate videos, deepfakes, and such. So the evolution is very, very, very fast. I call it like the industrial revolution version 2 or something like that, because it's very big. When we talk about generative AI in the form of LLMs, they are at the intersection of deep learning, what we're going to talk about these sessions, natural language processing, which is a field that has been developing for a very long time, which involves the ability for computers to communicate and interpret human language, and computer vision, which involves generation and interpretation of images using computers. And then deep learning is a smaller field of machine learning, which is a smaller field of artificial intelligence. We also have multimodals, LLMs, which can accept, besides text, can also accept images, audio, or video input. You can send an image to ChatGPT and it can interpret it. I will also have a demo at the end of the presentation where we will send to ChatGPT a slide from this presentation, and GPT will generate an audio description of that slide. Will basically present the slide for me. When we talk about size, these large language models are immense. They have billions of parameters trained on lots of data, like trillions of words in a lot of languages and a lot of combinations and things like that. We just have to remember that these models don't really think, they don't have conscience or anything related to that, even though it might seem so because they are so natural in their responses. At the base, they are basically just next word predictors. But we will explain that further in future sessions. So we have a first example. It's very basic. I think you all played around with ChatGPT. It is capable of generating new content. For example, I asked it to generate a short story that begins with a dark stormy night. And this is the short story, only a fragment of it. You can specify whatever you want. And the more specific you are, the better results you get. It is capable of translating text. Also, Google Translate is based on a large language model now, and basically all the translation, the big translation apps are based on LLMs now. It is also trained on generating code. You can write code on a multiple array of languages. Yeah, this is why nowadays it is important to keep our GitHub repositories private, because ChatGPT was trained on public GitHub repositories, and all the code was Stack Overflow and things like that. It can also translate code from one language to another. For example, here I asked it to translate into Fortran. I was not expecting it to be capable, but seems like it is very capable. I haven't tested this Fortran code. Yeah, it can also generate graphs and tables given an amount of data, or it can also create data, and it can also interpret the past graphs that it generated. It can also generate a text description. Here we have an example of a multimodal LLM where I set it a map of a shipment route, and I asked it to describe it. And you can see that it was able to detect that from the Netherlands to northern Italy, it was an air transportation because of the straight line. And after that, it described basically the itinerary in the northern part of Italy, which was more than likely by highway. And we can also generate images based on short descriptions. You can get very specific. Here I asked it to generate an image using a crafty textured look, and I think it looks very good. It is also very high quality. You see the resolution is quite high. Okay, let's see where it all started with neural networks. And neural networks and deep learning had a very consistent growth starting from 2015, 2016. We can see the blue line on Google Trends for deep learning compared to other machine learning terms, you can see that it has a very consistent growth, but everything exploded in the last few years with LLMs, with the purple line. And neural networks have been around for a very long time. I think the very first algorithm for neural networks appeared in the 70s. But everything was limited by the technology of that time. Nowadays, we have cloud, we have very high capacity storage options, and we have very powerful machines that can handle all this data. The applications of neural networks are many. These are just a few. Probably the most used field of neural networks are in recommender systems, like everything recommended on Netflix, YouTube, TikTok, Instagram Reels. Everything uses deep learning at its core. Also for marketing, for personalized ads, for security using facial recognitions. Autonomous vehicles also use deep learning or computer vision and things like that to drive themselves. Let's start with the most basic form of a neural network. It is called the perceptron, and it is basically a single layer with a single neuron here in the middle. On the left, we have what we call the input layer. This X is what we call the feature vector. For example, we can have like a two-dimensional point, then the feature vector will be those two dimensions, X and Y, or X, Y, Z for three-dimensional points, or however we decide to encode our input data. And for each element of this feature vector that is given as input, we have an assigned W weight. It's a weight. This is one of the parameters of any neural network. And the neuron will just compute the sum of products between the input vector element and the weight, its respective weight. This is the Z. And after that, it will apply what we call an activation function. In this case, we have what is called a step activation function. Basically, the output of the neuron, which is Y, is 1 if Z is higher than a specified threshold, or 0 otherwise. In other words, if Z is higher than a specified threshold, we can say that the neuron fires. If not, it remains inactive. I talked about the activation function. In our case, in the perceptron, it is the step function. If we were to visualize how the output of the neuron looks on two-dimensional data, it would look something like this. We have points from two separate classes. We have the red class and the blue class. In this case, on the left, we have the graph of the end function. And what our neural network does is classify these points based on the specified class. So for example, we can see that the red points are in the red class, and then the blue point is in the blue class. In the middle, we have the separation line that is defined by the network. This background that is colored like this, it's called decision surface of the neural network. And we can see here in the case of the end function that the perceptron was able to separate the two classes because the end function is linearly separable. But when we go to a function that is not linearly separable, for example, the XOR function, we can see that there is no way that we can successfully classify all of the points using a single line, a single perceptron. This is why we need a multi-layer perceptron, or these networks are also called dense neural networks or feed-forward neural networks. They are called dense neural networks because all of the nodes from one layer are connected to each of the nodes from the next layer. For example, we have a very simple architecture. Here we have 3 neurons on the hidden layer. This is what we call the hidden layer in the middle. We have the input layer, like I said, on the left. And we have the output layer on the right, the Z, the output of the network. Just like before, we have weights for each input and neuron. Here, what is also added is what we call bias. This bias basically is a value that is added to the output of the neuron, to the Z value before the activation function is applied. It can be either positive or negative. If we talk about the perceptron, that bias was basically the threshold value that the output needed to pass in order for the neuron to fire. And we can see here as an example, if we want to compute the output of neuron C, we do the sum of products between the inputs and their respective weights, and then we add the bias. And then to this value, we apply an activation function. We can see here that the output of the hidden layer is the input of the output layer. Sounds a bit strange, but if we were to have multiple hidden layers like this one here in the middle, then the output of the first hidden layer will be the input of the second hidden layer, and the chain continues until the end of the network. This is an example of an already trained network to compute the sum of two inputs, A and B. These weights were adjusted during the training in order for the network output to always be the sum of the inputs. Here we use, for the activation function, we use the max function between 0 and the output of the neuron. I can show you an example, a computation example. Like we see here, we compute the Z for this neuron by summing the products between the inputs and their respective weights, and then adding the bias. We do the same for all the neurons on the hidden layer. We then apply the step function, the activation function, in our case, max function with 0. And we see here, because we have a negative value, this neuron will not fire. Therefore, in our final computation, we can see that the output of this neuron will be multiplied by 0 and will not have any effect on the output. And the output will be, of course, the sum of 2 and 2, 4.000 and then something, because the prediction of the network is always something approximate but not exact. And then this approximation we will then interpret as our desired output. And if we were to have a different network with the same architecture, and then we initialize these values with these weights with other values, and then do the training, like we have here, different weights and biases, we will have the same result. If you are curious, you can check the computations and see for yourself. I will have the presentation ready for you at the end. And you can also check the computation to see for yourself that the output remains the same. Okay, let's start with the most basic concepts. We first have our data set that we want to train on. We call it the input data set. Like we said, we are using feature vectors for training. So for example, here we have two-dimensional points. The feature vector would be the x and y of.
You are on mute, Vlad.
Sorry, can you hear me now? Okay,
Yes.
sorry
Yeah.
for that. So the dataset will consist of all of these points. And whenever we train, we take each point, we take its feature vector represented by the coordinates, and we use that for training. Also, you can see that here in this dataset, we have two classes of points, the red and the blue. We encode this classification using labels. So for each element of the dataset, we have an assigned label. Here we can use an encoding like 0 for red, 1 for blue, or something similar. And this label is used together with a feature vector in the training process in order for the neural network to learn that I will say that this point with these coordinates belongs to this dataset. And then the network, after the training process, will learn the class of each and every point in the training dataset, and then it will be able to classify it using this separation line. If we talk about three-dimensional points, then the separation can be represented as a plane. The feature vector will be the free coordinates. We can also work with images, and then we encode the image, the whole image as a feature vector for each value of the pixel. This will be the feature vector. For example, we have an image 64 by 64, I think, or 32 by 32. We have a 784 size feature vector, and this feature vector will contain the grayscale value for each pixel. Here we are talking about handwritten digit recognition. We have multiple images of different digits, and the digit itself is the class of the image. So that will be the label, and the feature vector will be the whole vector of the grayscale values. Whenever we do training, it is important to do a split. We have the whole data set. It is important to have the training subset or the training data set that is used only for training, and then a separate data set that we don't include in the training used for evaluation, because we want our networks to be able to generalize on new data. Because when we train networks, yes, they are capable of learning the training data very well. But a well-trained network should also be able to give same results on new data that it hasn't seen so far. And this is what the testing subset is used for the evaluation of the network after training. Okay, let's talk about the training algorithm. Here, using this diagram, we have a neural network, a multi-layer perceptron or feed-forward network with a similar architecture to the one before. Going from left to right, so from input to output, we take first the inputs, we multiply them with their weights, we compute the sum of the products, we add the bias, we apply the activation function, and then the output, it is basically the prediction of the network. This process so far is called the feed forward or prediction step. This computed output or the prediction is then compared with the correct output or the label from the input dataset. And using what we call a loss function, we compute the loss of the network or the error. And using this error, we go back in the network and adjust the weights and the biases. These are the parameters of the network. We adjust them such that next time we get a lower loss or lower error. So we iterate this process multiple times, and our goal is to reduce the error or reduce the loss value of the loss function. So basically, we compute the prediction, we compare with the actual label, and then the error is used to adjust the network. And this is what learning is, using the error to adjust the parameters such that next time we get a lower error. Okay, Let's talk about these activation functions. They are important because they introduce non-linearity in the network. If we were to have a linear network, we will basically have a composition of linear functions, and we don't benefit anything from having multiple layers, because if we have composition of linear function is also a linear function, so we don't have any benefit from having a layered network. So we need something to introduce non-linearity in our architecture. It is important for these functions to be easily differentiable, because their gradients or their derivative, first derivative of the function, will be used in the learning process. This gradient or first derivative is used in the backpropagation step when we go back in the network and adjust the parameters in order to lower the error. These activation functions are also important because they can control the range of the output. For example, the logistic and the hyperbolic tangent function, you can see here on the graph, the logistic one has the output between 0 and 1, and the hyperbolic tangent has the output between -1 and 1. Okay. Let's talk about the third activation functions that we had on the previous slide, the rectified linear unit or ReLU function. The output of this function is the max between x and 0. So it's basically max between 0 and the input value. It has a very useful derivative because it is very fast to compute. So the learning process is very accelerated using these functions. It has constant gradients, which means that we don't have any problems if we have, how do I say? During the training process, these gradients will change over time. And if we have a lot of time smaller gradient values, then we have small adjustments for a neuron, and that means that that neuron might become inactive. This can be a good thing. It can also be a bad thing. Inactive neurons in the network is not necessarily a really bad thing, because it can introduce some sparsity in the network, and this can help with a problem that we call overfitting. That we will talk later about that. This is the gradient of the ReLU function. You can see that it is very simple, basically a step function with 0 threshold. One problem with this function is that because the output is unbounded, it can lead to some exploding gradients. So if we have very big errors, we can have very big gradients, and then the training can get a bit all over itself, but that doesn't really happen in practice. And for the problem regarding the 0 gradient for the negative values, we also have some alternatives called the leaky ReLU or parametric ReLU. These are the graphs. We can see that we no longer have a 0 output for negative values. We can use a small parameter or an exponential factor in order to modify the output of the activation function. The logistic function has output between 0 and 1, has a much more smoother output, and also the gradient is also smoother. You can see from the graph. One big problem with this is that the ReLU function didn't have. This one has this problem called vanishing gradient problem. We can see here that outside of the range -3 and 3, we have very small gradient values. So smaller gradient values means slow learning for that particular neuron, which can lead to that neuron becoming inactive. And if we have a lot of neurons like this, the learning slows down. And the hyperbolic tangent function is very similar. We use it when we want to have zero-centered outputs, meaning that the output is between -1 and 1. Yeah, very similar to the sigmoid function or the logistic function, but it has the same problem with vanishing gradient. Outside the range -2 and 2, we have very small gradient values. So it can lead to slow learning. The softmax activation function is a special case of activation because it is usually used on the output layer when we might have to deal with multiple classes. So if we have like, for example, like the example that I showed before with handwritten digits, then we have 10 classes from 0 to 9. And the output of the network will have 10 neurons. And if we want to interpret for a specific input, if we want to interpret what that class belongs, what class it belongs to, then we can use the softmax function that takes an input and the output will be a probability function, probability distribution, sorry, because the output of the softmax function always sums to 1. So for the handwritten digits, we can apply the softmax function to the output, and then we get a probability. So if we have something like this, we will talk about, we will see here that we might have 5 classes, we have 5 probabilities. You can see here that this value is the highest. So we can safely say that that specific input belongs to the second class, because this is what the probability for the second class is. And this is the highest. This one is very, very useful for multi-class classification, like handwritten digits and everything that has multiple classes. And please remember that this one is only used for the output layer when we want to have a probability distribution. Okay, this is a summary of the activation functions. ReLU is the most popular for hidden layers. Fast to compute, simple, works well in most of the cases. If you need special cases where you don't have where you don't want 0 for negative values, then you use the other variants for the ReLU function. And then sigmoid and hyperbolic tangent, you can also use them for binary classification or regression, but they are a bit slower. Okay, let's talk about the loss function. They are also called cost functions. Like I said, the role of this function is to quantify the error of the network, meaning the difference between the prediction and the actual value of that input. So if we talk about digits, the prediction can be, I don't know, 3 point something, 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 and the actual label is 4. Therefore, the error would be something between 0 and 1, a small value. That is the loss function output. And that is what we'll use to learn, to adjust the parameters in order for the network to learn. If we were to have a network that only has 2 parameters, so 2 weights, and then we plot these weights on 2 axes, x and y here, and then for each combination of values between a range, of course, of these 2 weights, we then plot the value of the loss function. Then we get something like this, is what we call a loss surface. And training basically means navigating this loss surface in order to reach the global minimum of the loss function, where we have the minimum error and maximum accuracy. Whenever we start training and we initialize parameters, we can be situated anywhere on this surface. We can be here in the peak, we can also be near the bottom. Training means navigating this surface in order to reach the global minimum, in order to reach it here. We can also have some problems regarding local minima you can say that, or you can have training where you reach a minimum value, but it is not the global minimum. How do you continue training in order to reach the global minimum? We will talk about that on Thursday when we will discuss different training optimizers or training algorithms. But please remember that minimum loss equals to maximum accuracy. And our goal is to minimize this loss during the training. From one iteration to another, we want to have lower and lower loss values. Mean squared error is the most basic and probably one of the most used loss function. It resembles the formula for variance, which computes how far elements are from a specific mean. You can see here that we first do a difference between the output. Y is the output of the network, the prediction. T is the label of that instance, or the ground truth, or whatever you want to call it, is what that class is supposed to be. And then we have a sum squared, and we also divide by the number of training instances. This is the formula for the mean squared error. We also need its gradient for learning. It is easily differentiable and fast to compute. This gradient is useful because it penalizes large errors. This loss function is useful because it is a convex function, which means that it has a single global minimum. So we don't have local minima with this function. Because it penalizes large errors, it is very sensible to outliers. Outliers means that points or noise in data, you can also call that, which shouldn't be there, but in most of the cases, we get noise whenever we collect data. And this loss function is sensible to noise. We also have cross entropy. It is best used with a softmax function for the output layer. Useful for the multi-class classification tasks. Can also be adapted to binary classification tasks. It's not the same as mean squared error because it has output between 0 and 1, values closer to 1 for large errors, values closer to 0 for small errors. It is also convex, but can be a bit sensitive to imbalanced sets where we have a larger class, significantly larger class than the others, or any sort of imbalance in this sets, in the data set. Okay, let's talk about the gradient. Like I said, the gradient is also called the first derivative of the function. Why do we use the gradient? We use it because the gradient or the first derivative determines the slope of the tangent of the graph for a function. In other words, the gradient basically points to the direction of the greatest rate of increase. Therefore, if we want to minimize the loss function and we use its gradient, we need to go in the opposite direction. Because we want to reach the global minimum. And this can be seen here in this animation for a convex function, how the gradient is, or the tangent helps us reach the global minimum. So, having said this, let's talk about the actual training algorithm, which is what we call backpropagation with stochastic gradient descent. Gradient descent means that we want to reach the global minimum using the gradient. And backpropagation means that we backpropagate the error into the network in order to adjust the weights. So first, we compute the prediction of the network. We then compute the loss or the error. We will use the gradients of the loss and the activation function on each layer in order to backpropagate that error and adjust the weights. Adjusting the weights is done by multiplying the error with a small rate called the learning rate, which has values usually between 0 and 0.5. I will show you in a future slide what a bigger learning rate leads to in a visual representation. But it is obvious that learning rate that is too small will lead to slow learning, but a big learning rate will lead to fluctuation in the cost function, and then the global minimum is overshoot or is missed. This value of the learning rate, we usually start with a small value, and then we adjust it empirically by testing with different values to see what we get. If we get a faster learning, or if we get slow learning or overshooting, we need to test in order to find the best value for the learning rate. But if you are between 0 and 0.5, that is always a safe bet. Like I said, these are the steps for the training. These 4 steps represent a training epoch. So after you have done these 4 steps for each and every element from the input dataset, you have completed a training epoch. Usually training spans over a number of repeating epochs, usually hundreds, tens, hundreds, thousands, whatever the case may be, depending on the size of the dataset and the size of the network. But it is important to understand that we do training for each element in the dataset. After we completed the dataset, we repeat it again, what we call an epoch, and then do it all over again. This is what the training procedure looks like, repeating the same thing over and over again until the loss value is minimum and the accuracy is at its highest. What I explained so far is called classic training, where we adjust the weights after each element from the dataset. So we learn, we process one element at a time. But this can be a problem with noisy data. Like I said, when we have a lot of outliers, this can make modifications in our network that we don't want. So this is why mini batch training was developed. It involves splitting the dataset into smaller chunks, and then we use these chunks as a whole for adjusting the weights. What is the pro of this use case is that it is a lot more stable, because if we have a mini batch where we have some noise, this noise will be averaged over all of the elements from that mini batch. So we don't really have problems with noisy data. It can be a bit slower, but using GPUs, like you might know, training is usually done using GPUs or graphic cards, which can make use of parallel computing. This problem can be solved. So it's not a problem using mini batches that it is slower. In contrary, with modern frameworks, mini batch training is usually faster than classic training. And it is also very useful for a large dataset because it's a lot more memory efficient. These 2 animations present us how gradient descent looks visually with different values for learning rate. You can see on the left side, we start from somewhere on this edge here, and we want to reach the global minimum with an adequate learning rate. We have a steady descent on the bottom. But where we have a larger learning rate, you can see that the training is all over itself. This is called, like I said, overshooting. We do modifications in the network that are too big, and then we get fluctuations in the loss value over the training period. Okay, one more thing I would like to talk about today is also called overfitting. So what is this overfitting? Let's start by repeating the fact that The purpose of training neural networks is that they are capable of accurately predicting new data. If a network can only predict on the trained data, but not on new data, we can say that that network was overfit on the training data. The main cause of this overfitting issue is that either the training data set is too small or is not varied enough, or both. Some solutions to this problem include increasing the data set, which means basically getting more data, which can sometimes be impossible or very costly. We can do we can overcome this by generating some new data from the existing data set. For example, if we were to talk about images, we can generate new images by applying different effects on the original images, such as slight rotation or skews or blurring or a bit of translation. But this can lead to a way too large data set and can become unpractical because larger data set means larger data and longer training. And maybe we don't have enough computational power for that. Overfitting can also appear when the network is too big for that data set. So one method is to reduce the number of neurons or have something that implements some kind of sparsity in the network. If you want that to be more precise, then we implement something called dropout, meaning that at each epoch, we select a random batch of neurons to be ignored. So they will not take part in the learning process in that epoch. In the next epoch, we have another random batch. And this can help a bit with overfitting. Overfitting also appears when the weight values increase too much or they have very big fluctuations. So another technique is called the regularization, is to penalize large weight values, basically implement some kind of threshold mechanism or something like this. There are a lot of regularization techniques out there. This is what overfitting looks like on a two-dimensional data set. You can see here that the network is able to distinguish between each and one of the point from the data set. Of course, it has low loss and high accuracy on the training data set, but when we introduce new points that are not here, there might be some problems, and then we will have low accuracy. On the left, we have an example of an underfit model that was not trained enough. It is not able to distinguish at all. And then on the right is what looks like a better fit. You can see here that there are some small noise that it is not classified correctly, but having a network like this means that it is able to generalize on your data, and we keep the accuracy from the training also on the test data set, validation data set, whatever you want to call it, the one used for evaluating the model. Okay, I think this is enough for today. I want to show you a small demo, the one that I talked about, involving having a slide from this presentation described by an AI model. Let me show you the result. I think this speed is. Please let me know if you don't hear the sharing. Let's see, share sound. I think you should hear it now.
Today, let's dive into the concept of loss functions, also known as cost functions. These functions are crucial in evaluating how well or poorly a neural network is performing, particularly regarding its predictions. Essentially, a loss function quantifies the error by measuring the difference between what the network predicts and the actual target values, or the ground truth. Our main goal in training the network is to minimize this loss function. By doing so, we're effectively working towards achieving the most accurate predictions possible. As you can see in the graph to the right, we encounter various points like local minima, saddle points, and global minima. Our aim is to reach that global minimum because that's where our model's error is the lowest, leading to maximum accuracy in predictions. By focusing on minimizing the loss, we're enhancing the model's performance and reliability.
I hope the sound was shared okay. You could hear the description of the slide. It was very good, very accurate, a good pacing and good explanation. I think it's even better than myself. If you are curious, the application for this use case is very small. This is the backend, 75 lines, around 120 lines of Python code using the GPT API. And I don't know, 200 lines for the front, something like this, including CSS and the HTML. And this is the whole app, which can get as input any image, and the model will describe whatever is that on that image. The steps for this application is feed the image into the GPT API. The GPT will then output a text description, and then the text description will send it to another model, text-to-voice model, in order to generate the audio description. Okay, this would be all for today. Thank you for your attention. I hope it was interesting enough. I hope it was not too technical. I tried to reduce the math to a minimum, but also keep the important stuff. If you have any questions, please, you can write them in the chat or ask me directly.
Okay, so thank you, Vlad, thank you, Christian. While we wait for questions, let me remind you that we have a second session on Thursday, same time, and as part of this session, you will also have a code walkthrough and also some resources shared, so you can actually start practicing yourself. So looking forward to meet you on Thursday as well.
I will send on this chat here for this presentation and this call. I will send a link to what is called the Jupyter Notebook. I will show you how it looks like. No, just a moment. I'll start sharing my screen again. So this is what we will be working with on Thursday. This is what is called the Jupyter Notebook. And this type of writing code is very useful because, first of all, you have everything on cloud. You don't have to install anything. You just need a Google account with connection to Drive. You can then take this whole notebook, copy to your own Drive account, and then start playing around with Python code. And what is very great about this Jupyter Notebooks is that these blocks right here of code can be run separately. So for example, this block here has some Python code that is used for imports. If I'm running this block, then the imports are done and I don't have to run them again. The runtime has the imports available for me anytime, and each block of code has its own output. Yeah, so it's very, very nice for didactic use cases, and it's very nice that you don't have to install anything. This is what I will show you on Thursday. I will send you the link to this notebook if you want to have a look before, to familiarize yourself with the notebook and the Python code. And there is also a lot of text here that explains everything. You can do that until the presentation, but I will also do that. On Thursday, we will have a deep dive on this notebook. That is basically a small example of training a neural network on some bidimensional data. This is the data that we'll be working on, and this is how the output should look like in the end. The decision surfaces for this data set. So let me send you the link. I will also send you the presentation. If you have any questions, you can hit me up on Teams anytime, and we can do a call, look, discuss whenever you feel like it.
Also, I will share a link to show you what we discussed here today about the neural networks, to show you that LLMs, how it's the architecture of this, and to see the weights, the biases of LLMs, to have an idea how it looks.
Okay, yeah, yes. We will also look into this in our next sessions next year. We will do a deep dive into that. Okay, then, this would be all for today. Thank you all for the attention.
I have one question, sorry.
Yes, please.
Oh, because today there is a lot of information for this. So, is there a way to try and practice by ourselves, step by step, to see?
Yes. So we will do training by writing Python code on Thursday, by looking and analyzing this notebook that is run by me. If you want to play around with a more visual approach, you can search for TensorFlow Playground. I will also send you a link where you could do visual training. It looks something like this. This is basically a neural network similar to the one that we discussed. We are doing classification on two-dimensional data, so these are the inputs. You can change the architecture of the network, the number of layers, the number of neurons on each one. You can change the activation function for the hidden layers. You can also apply regularization, like we talked that for overfitting, and also change the learning rate. And if you start the learning, this is how it should look like. So I will send you the link for this one. I will also do a demo with an application similar to this, but it has more use cases. That application was done by me for the bachelor's degree. We will do that on Friday, but if you want to play around until then, I will send the link here in the chat. And then the specific steps for doing training, I will show them in this notebook, and then you will have the notebook. You can also have it from today and play around for yourself. There are lots of data sets that can be loaded using this PyTorch framework that I will show you on Thursday. You can load already prepared data sets for learning and didactic applications and play around for yourself. But I will send all of the useful links here in this chat.
Thank you. Thank you very much.
Thank you for the question. Thank you. Any other questions, curiosities?
Yeah, I have some question.
Yes, please.
Well, this was really a great presentation for neural networks, but I have a question. These neural networks are known for last 50 or 60 years, and this what you explained is basically classical applications for neural networks, which is already known. But I'm currently missing a gap. Obviously, something happened in the last few years when we have ChatGPT, and we didn't have GPT 10 years ago. So what's happened? And maybe it will be covered in next presentations. But okay.
We will cover that in the presentations in the next year. These two presentations, I wanted them to give everyone an insight of how neural network works internally and how everything started. And after that, next year, we will do a deep dive into more complex architectures like transformers, recurrent neural networks, and things like that, that are the base of these large language models and how they look on the inside. And we will also do a lot of practical applications by playing around with GPT API, Google Gemini API. Maybe we can do a bit of training on a local LLM ourselves. I have to check if that's possible with the available computing power, because these large language models, like their names say, they are very large, billions of parameters. So you need a lot of computing power to run them manually. But they are open source. You can download such a model and do some training, do some fine tuning, prediction. Yes, but the best use case is doing it by using the API from GPT. And we will also show you how you can customize specific agents for a specific reason. This is what GPT is calling them, agents. You basically generate an agent, and then you give it some knowledge that you want answers on. You can give that knowledge in the form of PDF documents or however you want to encode data. You just send them to the API. It will learn on that data, and then it will only respond with specific questions from that knowledge base. But we will do that in future presentations. For now, I just want to show you the basics. Okay, any other questions? If not, I think we can close the call. Thank you again for the attention. Thank you for the questions. I hope it was catchy enough and not too technical. I will leave all of the useful links here in this chat. Like I said, I recommend you to have a look on that notebook before we deep dive on Thursday, just to familiarize yourself with how everything works. Let me show you one important step. When you first load into the notebook, if you want to save the progress, if you change anything in the notebook, if you want to save it, you need to copy it to your drive, and then this file will be saved on your Google Drive. And here is where you connect to a runtime. I recommend using changing the runtime type to T4 GPU, so we have faster learning. But we will also do that on Thursday. Okay. Thank you very much for your attention, and see you on Thursday, and see you tomorrow at All Hands.
Thank you.
Thank you. Have a good
Bye.
day.
Thank you.
Bye.
Bye.
Thank you. Bye-bye.
Bye-bye.
Thank you.